Let's say if you have 7 Harry Potter books, like this, on your bookshelf. Let's say if you have, I asked you a math question. How many different ways are there to arrange these 7 books? Do you know the answer?
7 times 4.
Great. 7 of you do not know, or 2 more just to say how. Now, when you have a problem like this, usually it is hard. Pretty easy. Good. Then, for those who do not know, the answer is 7 factorial. The one thing I'll recommend you to think about, let's say the law of the ring, with only 3 books. Then, after you spend whatever number of minutes, you can generally probably figure out, okay, there are this many ways to arrange kind of 3 books. Which again, someone said this is 7 factorial, this is 3 factorial, this is kind of 3 times 2 times 1, and then this is 7 times 6 all the way times 1. Okay? So let's kind of start talking about math, but if there's only one thing that you make out of the math circle, whenever you have a problem that is difficult, change the number to a much smaller number, and then after 3, if you still don't get it, try 4, and then usually that's when you start seeing the pattern of the question, and then that will help you answer the original question. Okay? Cool. Let's kind of start talking about the math. So the first part is what I call set theory. Okay, so the first part is what I call set notation. Okay. So a set is basically a collection of elements notated by some curly brackets, like this one. So let me give you a couple examples. For example, this is a set A, and it could have just kind of 4 elements to it. 1, 2, 3, 4. Okay? Now, inside the set, there can be things other than numbers. For example, it could be just a name of some common fruits, like apple, oranges, grape, and cherry. Or, I'll give one more example. It could just be name. Daisy, Donald, or Mickey. So far so good? Now, it is a convention that we usually use kind of capital letters to describe the sets, like A, B, and C. And we usually kind of use kind of small letters to describe the elements. Now, if I say X is equal to 1, Y is equal to 5, as an example. So there's a new notation that will basically say X is inside the set A, whereas Y is not in the set A. Because 1 is inside, is one of the elements, and 5, which is Y, is not one of the elements.
Is that an E?
This is a notation. This is a symbol, like this. It's a shorthand for is an element of. Okay, no one raised any sign yet. Great. So let's keep going. I'm going to erase this. So next, let's give just a few more examples. Let's say if I define another set of D that is all first names. The second letter is a vowel. Now, for the set ABC that we talk about, as you can see, we basically write out what those elements are explicitly. But now it is another way of describing it. This kind of colon, you can basically read the kind of colon sign as has the property or have the characteristics of. Okay? So D is all first names that also have the properties of the second letter is vowel. For example, Daisy is another example because Daisy is the first name and the second letter is a vowel. Okay. Here's another set, E. X is an element of D. And it also have another property. The first letter is a vowel. Can someone give me an example of an element inside the set E? Good job. Let's kind of go back to some mathematics example. Let's say it could be x is an integer. And it's also between 3 and 17. Okay. So now, let's say we have a symbol. If you put two vertical bars outside the set S, so it's counting the number of elements of X. Using this symbol, then we know the set A has 4 elements. Because at the beginning, A is 1, 2, 3, 4. So there are 4 elements. What about F? Yep, 15. Okay. So the last thing I want to talk about in this kind of subsection of set notation is just another terminology. Okay. So sometimes the elements of a set are sets themselves. For example, so this is an example of a set which has 2 elements. The first element is a set 1, 2, 3. The second element of the set is another set with 1 and 2. So here's another example. Let's say a set B, and it has 3 elements, which is the set A, B, C that we talk about. Now, because when you talk about a set of a set, which sometimes can be confusing, so there's a convention that we will basically call this a collection. So when we talk about a set of sets, usually basically we'll say B is a collection of 3 sets, A, B, and C. And this is another convention, small letter for the elements, capital letter for set. And then when it is a collection, usually people will use kind of script letters to represent this. So this is why it's A and B. Okay, time to take a vote. So this is the end of the first subsection, set notation. Can everyone kind of give me a vote? Can you ask question? Which part is it just towards the end, or which part is confusing? Hmm?
The elements of a set in the set.
The elements of a set?
So like the sets in a set.
Oh. Let me try. Think about when we go to grocery stores, okay? So we have a bag of groceries, okay? And let's say inside there can be fruits, like apple, or it can be orange, or it can be grape. So basically, this is what we call a bag of groceries, okay? Which is everything until I talk about collection, basically a set or a bag of groceries. Sometimes in groceries, you have multiple bags of groceries, and then you will basically have a really big bag carrying this. So the way to describe this is now I have a bag of bags of grocery. Okay, are you with me so far? So because the phrase a bag of bags can be very confusing, because we use the same word bag to both refer to the big one and also the smaller one. So here we introduce a new terminology, which is if the bag is big, inside is kind of different bags of grocery, we call the outer one, we call it a collection. So instead of saying a bag of bags of groceries, now we have a new terminology, which is a collection of bags of groceries. But it both means just a container.
What is the notation for a collection again?
What is the notation for collection? It usually basically uses script capital letters.
We can learn those letters?
Hmm?
We can learn how to write those letters?
So this is A. Is that your question? B. Basically, use your calligraphy to write the capital letters. Does it help? Questions? For the girls, can you raise your sign again? Is it getting a little better? Cool. So we are pretty good. Well, actually not that good, but we're okay on time. So let's move on to the second part. The second part, now, the second part is 1.2. Is what I call set operations and relations. Say that again? Oh, okay. So set operations, we're going to talk about a few. So A and B are two sets. Sometimes we graphically draw some picture for us to think about how the two sets are related to one another or not. There are kind of a few examples. In the first example, so what this means is we have two sets, A and B. There's some overlap. An example could be, let's say A is 1, 2, 3. B is, let's say, 3, 4, 5. Then in that case, using this would be, we have a 1 here, 2 here, 3 here, 4 here, 5 here. Okay? But there are other possibilities. For example, A and B can be completely unrelated. There's just kind of no overlap. It could also be one containing another. In two different directions. Okay. So now let's kind of explain what this kind of four symbols means. The first one is what we call union. And the symbol is like a capital U. So A union B this is the definition of A union B. So I use another kind of new notation, but this vertical bar, you could think of this as the same as just a colon, meaning a description of what the set element is. Now, A union B, it means, you definitely did not see and, it means or. So A union B, that means the elements can be either in A or in B, or both, okay? Now, another operation called intersection is the upside down of a capital U, if you will. It has to be in both kind of A and B. Now, one thing that if you learn this kind of set theory in the future, when you in math classes, they always kind of use this as an example. Okay? What I meant by that is, oftentimes, what you see is as follows. A union B would be represented as A union B would be represented like this. and A intersect B would be represented like this. Again, intuitively, it means it's okay to be either in A or B or both. For intersection, as the word kind of intersection suggests, it has to be in both A and B. But one thing that everyone should always remember is A and B do not necessarily look like this. So what I meant is this picture implied there has to be something here. But it is always possible that A and B are completely unrelated. So in this case, I'm going to erase and then kind of draw it. So one thing is remember is it is possible that A intersect B is an empty set, meaning that there's nothing inside. Again, think about the picture. A and B is completely not related. An empty set happens pretty often, so there's a special symbol for it, which is this. Okay. And the way to describe this situation, when A and B are completely not related, there's no common element to it, we call that they are disjoint. So we talk about union, we talk about intersection. Let's talk about minus. So A minus B. Meaning the element is in A, but not in B. So using this example, in A, but not in B, that would be this, okay? Again, let me just reiterate, this is kind of what helps us to remember what it means, but A and B can be in any of the kind of 4 configurations that we talk about. So the next one is this cross, Cartesian products. So this is the part of the mathematics that, in my opinion, more advanced students might have more difficulties understanding this than the younger students in class, okay? And I'll explain why. So Cartesian product, so you have 2 sets, again, A and B. It's basically a notation that we said we want to have 2 elements, what we call order pair, and this is what we call Cartesian product. Let me give an example to illustrate what this is. Let's say if we have a new set again, G, and it has 2 elements to it, duck and mouse. if you go back to your notes, C has 3 elements in it. Daisy, Donald, and Mickey. Then using this definition, can someone tell me what are some of the example of elements inside this? So we have Donald, duck. What else do we have? We have Daisy duck. And then we have Donald mouse. And then we have Daisy mouse. And then we have Mickey duck. And Mickey mouse. Let me take a pause. How's everyone feeling so far about this Cartesian product, like Donald duck, Daisy duck, Mickey mouse? So it is a new notation. Anyone? Raise your sign. How are you feeling? The rest of the class? So many of you say is okay. Question?
What if the same thing is in both sets?
Can you say your question again?
What if the same thing is in both sets? So maybe Mickey is in both sets C and G.
So you're saying what if, but the way that I define this C and G is the second element. You can only choose from duck and mouse.
Yeah.
But are you saying that if you have a C and C, then what happened?
So in assume set X, right, has 1, and then other numbers, and then set Y also has 1, but other numbers. So when you do the Cartesian product, and then you have would you have 1, 1?
Let me come back to this in 2 minutes. But that's the question why I said more advanced students tend to have confusion at this point. I'll give one more example to see if that answers your question. The second example is actually what you just said. Okay. Let me give you another example. X and Y. And X is the set of number. 1, 2, 3. Y is 1, 2, 3. And then I define a Cartesian product, X and Y. So in this example, we have an element 1, 1, which is in this. Is that the question you asked?
Yeah.
Yeah. So it's possible. Now, so far, the point that I try to illustrate on this Cartesian product to create a new set, like a new set, which is that 2 element, is a lot of you have a lot of association or imagination of what I just covered. For example, many of you, when you see this, you would immediately think about what you might have learned in school, that you have some coordinates. This is kind of 1, 1, this is 3, 3. Can I get a show of hands who know what Cartesian coordinates are? And the rest have not seen this before? No, okay. What I want to illustrate is when we define this, we have not added any meaning to this set. We literally just say, okay, let's just kind of have a bag of stuff defined by this way. But some of you might look at this to say, for this first example, some of this makes more sense than the other, right? Like 3 of them are more popular than the other 3. But the reality is, when I kind of talk about this, I didn't even tell you, like, this is the first name, this is the last name. So for those who already learned Cartesian product, when you see this, you immediately in your head are thinking about, oh, this is, let's say on a plane, the coordinates of a point on a plane. This is actually kind of hurting your understanding of this. Like, so far, I really did not add any meaning to any of this. I'm just saying, okay, you have a new way of creating a bag of stuff, which has 2 elements to it. So to kind of finish the second subsection, so I want to introduce one more notation, which is very simple, which is this 2 symbol. Whenever you have 2 sets, you set A is a subset. So this symbol is called a subset of B. If it is like this. Anything that is in A is also part of B. Okay. Another way is we basically say this: B contains A. So this is the relations between 2 sets. I'm going to keep my promise. Let's kind of take a break here.